Good day, students. Welcome to the third recording, still a continuation of determination of minerals. But in this section, we're going to focus on the analysis of sulfur dioxide in food products. Okay, so sulfur dioxide and its derivatives are actually known as sulfides. So they are known as sulfides, but when these sulfides, like your potassium methylbiosulfide, your sodium methylbiosulfide, when they are actually dissolved in aqueous medium, they liberate sulfur dioxide. So it's actually the derivatives of sulfur. So these are actually food additives, and we all know that food additives are chemicals, whether natural or synthetic, that are added in food to enhance different attributes in food. What they can do is that they can actually improve the nutritional value, or addition of, let's say, ascorbic acid in a food product, so that you want to increase the vitamin C content. It enhances the quality. It also helps in terms of consumer accessibility, because then when you're adding some of these food additives, they increase the shelf life of food, and in that way the food is actually available throughout the year. And then also, when adding other types of food additives, you can then make a variety of food, like food colorants and food flavorants. They are actually food additives, so you can have a variety of different flavors of the same cool drink. So in that way, people can have a variety. But when talking about sulfides as food additives, we're talking about them being preservatives and antioxidants. So sulfides are actually added into food, different types of food products. They are added there, and they have multifunctional roles. Sometimes when you talk about preservatives, they will just have one function. There will be just an antimicrobial. But when we talk about sulfides, they have multifunctional roles. They are antimicrobials. They are used in food products, especially in wine and juices, to prevent your microbial growth, like mostly your yeast during fermentation, and also preventing yeast from growing in there, and some microorganisms, bacteria. And then they also act as enzyme inhibitors, like when enzymatic browning takes place, when you see an apple or a banana bruising, they can actually prevent that type of reaction. It's called enzymatic browning. They also act as an oxygen scavenger, so they are actually antioxidants in such a way that when your oxygen wants to attack food molecules or any molecule, what they do is that they can then react with the sulfides. That's why it's called a scavenger of oxygen, and therefore it works hand in glove with the enzyme inhibitor, but with other properties also when it comes to that. It's something that you will do in third year, so we'll talk about that then. And also important, they also inhibit what we call non-enzymatic browning, something that you also do in third year. So you can already see that sulfides are very important in food. There is no way that we can actually then substitute them with other type of food additives. Okay, so but one thing about the sulfides, like I already mentioned, when we talk about sulfur dioxide or sulfides, we're talking about different species of sulfur, or when you take your sulfides and then you dissolve them in aqueous media, and then those are collectively known as sulfides. But when dissolved in water, they liberate your sulfur dioxide. Okay, so in terms of the different types of products that are formed during sulfur dioxide, when it's actually when your sulfides are actually dissolved in aqueous media, you get your sulfurous acid, then you get your bisulfite anion, you get your sulfite and your metabisulfite. So these are the different species that then liberate sulfur during a reaction with water. And these are the type of additives that are then used in food. Just like anything else that is used in food, that is added to food, has to be regulated. So it is actually regulated in terms of adding sulfides in food, that when you are using sulfides and you are using more than 10 milligrams per kilogram in a food product, then that has to be declared, and that is actually based on the Foodstuff and Cosmetic and Disinfectants Act of 1972, and this is based on the regulation that's relating to the labeling and advertising. So we usually call it R146 of 2010. So then if you are using your sulfides and you are adding it in food and it's at 10 milligrams per kilogram, so that's 10 parts per million or more, then you have to declare it on the label. And secondly, if it happens that you were using sulfites, because they actually also use sulfites as what we call a processing aid. Let's say they are peeling potatoes. You know, when you're peeling potatoes, it might happen that they turn brown before the actual whatever process that you want to do. Maybe you want to fry them for Simba chips. So, but whilst that is still happening, they might turn brown. So you can then immerse those potatoes in sulfur dioxide or sulfites to prevent the onset of browning while still preparing. But eventually what happens is that those sulfites will end up in the final product. So in that way, whether or not you had added it into the final product, you used it as a processing aid, you still need to then declare it. So you declare it when you use 10 milligrams per kilogram or more, or when it actually got into the final product unintentionally. So that is what the regulation relating to foodstuff and labeling requires you to do. And also at the same time, following the regulation, there's the regulation that's governing your preservatives and your antioxidants. That is R965 of 1977. In there, it actually lists all the different types of food products where your sulfites can be added, and also the limits. So it can tell you that if you are using sulfites in dried fruits, you can use it at 200 milligrams per kilogram. If you are using it in wine, you cannot add so much. So those are the two regulations that you need to get used to. So although your sulfites are also not proteins or organic matter, what happens is that they actually, you already know things like your soy, your gluten and stuff, they produce allergic reactions in people. Same applies to your sulfites. That's why it has to be labeled when it's used at higher concentration, so that people that are allergic to sulfites can actually be able to make an informed decision as to whether they want to consume that food product. Especially people that are asthmatic, it has been found that when you have sulfites in food, then it actually rises to the top. You know, when you have your cool drink at the filling top, it rises there and concentrates there. That's why they will usually say shake before you use. And then when it's concentrated there, when you open the bottle, the first gulp that you take in too much sulfites, and it has been has had problems with people or affected people that are asthmatic or asthmatic, however you pronounce it, and it affects their respiratory, and some people also it affects their skin and everything else. You know how allergic reactions go in terms of different people. So that also becomes a problem. So it means that based on all that, it means that we need to then regulate how much of it goes into the food, and by doing so, it means that somebody has to be monitoring how much of the sulfites is being added in food products. So that is why we have to do the determination of sulfites. Okay, so this is just pictures showing different types of, it's a practical that we did in third year, but what I wanted to just highlight is the use of sulfites as antioxidants and anti-browning properties in vegetables and fruits. So you can already see this is juice, this is apple juice that was extracted or pressed, and then you can see that potassium metabisulfite is amongst the best in terms of preventing browning both on the fruit and the juice, and it's comparable to pasteurization or sterilization in ascorbic acid. And then you still see here the same thing happens. So this is just to prove what I've been saying, that it actually acts as a preservative or as an antioxidant, preventing some deleterious chemical reactions. So we'll probably do this later when you're in third year. Okay, so in terms of sulfur dioxide, when the sulfur dioxide is added into food products, it is then divided into what we call your free and your bound sulfur. So let's say you are adding 100 milligrams of your sulfites, whatever type of sulfite, in the food. What happens is that not all that 100 milligrams per kilogram or whatever will be functioning or having those properties whereby it's an antioxidant or it is a preservative, because some of the sulfites will be bound, and when it's bound, it's not available. So what happens is that's why we actually classify sulfites into free and bound. So we make an example of sulfites in wine. So the sulfites in wine, this is the free sulfites. So we already mentioned in the sulfites, the sodium sulfur dioxide, when it's actually dissolved in water, it produces different species, whereby you actually have your different ions of sugar, of sulfites. Therefore, you get your sulfur dioxide, you get your sulfurous acid, you get your bisulfite, and then you get your sulfite anion. So what happens is that in the whole wine, when you have both the free and the bound, this sulfur dioxide and the sulfurous acid, they are the ones that are active. They are the antiseptic, or antiseptic, obviously, you know, septic, it means contamination. We can say that's the one that gives the antimicrobial properties. However, your bisulfite is usually bound to your acetaldehydes in wine. Those are obviously other components that are found in wine. So your bisulfite can react with your aldehydes in wine, your dextrins, those are sugars, your pectic substances, your protein ketones, and certain sugars and other additional compounds. So not everything is going to be available. Okay, and then you get your sulfite, which then reacts as an antioxidant. Okay, and that one then is what we call your glucose sulfite. So what I'm just trying to explain is when you have your sulfites, some of the sulfites in there, I made an example of 100 milligrams. So in that 100 milligrams that you add, some of those will be bound. We can say maybe 60 milligrams will be bound to those components that I mentioned in wine. And then the rest of the 40 milligrams will be the one that is active to perform the function. So in that way, that's why when we analyze for sulfur dioxide, we actually analyze free sulfur dioxide and total sulfur dioxide, because then we can be misled, whereby we have 60, maybe for microorganisms not to grow in a food product, you require 100 milligrams. But then you add the same 100 milligrams, but then out of that 100 milligrams, 60 is bound. So it means you only have 40 milligrams, and that will not be enough to obviously reduce the number of microorganisms or prevent the microorganisms growing. So that's that. So we already mentioned that sulfur dioxide and its derivatives, I mentioned sodium metabisulfite, potassium metabisulfite, and so they are used in food processing either before or after as what we call processing aids and as antioxidant and antimicrobial. I'm just actually recapping what I said there. They have what we call GRAS status when they are used under the conditions that is specified. If you are told you need to use it at 200 milligrams per kilogram in fruit juice, then it's at GRAS status. It's generally regarded as safe. But if you're going to use 1,000 milligrams, then it's no longer safe. So GRAS status does not necessarily mean that it might not be toxic, but it can be toxic at higher doses that are not specified for use. Like, that's why I mentioned that it has to be within the legal limits. We mentioned the labeling regulation and then the regulation governing your antioxidants and preservative levels in food. And then, as much as all those other food products are mentioned that you can use your sulfites in your jam, you can use it in let's say your fruits, your prepared fruits, it is illegal to actually add it to meat. And this meat means your raw meat. But things like your processed meats, can actually be used in processed meats, but it cannot be used into raw meat that is going to be cooked. But processed meats, it can be used in there. It's illegal. So if it's added in food, that is illegal. So then, as I already mentioned, that since this is something that's very important, it affects the functionality, the attributes, and most importantly, something that we look out for, the shelf life of food. Therefore, we have to monitor it, and by monitoring it, we have to analyze it in food. It's a very simple, straightforward process whereby we have your sample that is suspected to have your sulfites or contain any derivatives of sulfites. And then what happens is that we then add your sulfuric acid, and then titrate it against your iodine until all that sulfuric acid is no more to produce your sulfuric acid. And then in that process, it's actually a titration method whereby we use starch indicator, whereby when the color changes blue, then you already see that all the iodine has been consumed. And then from there, based on that, using a standard, you can then calculate the amount of iodine titrate against that standard. And then you can actually calculate the amount of sulfides or sulfur dioxide that's found in the sample. It's one of those very straightforward, simple reactions. But then when this is actually just for your free sulfur dioxide. But then if you want to do your bound sulfur dioxide, you go a step further, and then I'm going to explain that in the ammonia method. Okay, so we are done with sulfides. After sulfides, the last one, which I'm still going to include here, is the bar value. The bar value is known as the Brix-Acid Ratio. So what this actually means is that the Brix-Acid Ratio is the ratio of the sugar and acid in fruits. And this ratio or bar value is actually used by your farmers as to when is it the right time to pick fruit. They obviously have their ranges whereby they want to see if the fruit is ripe, because as your fruit is still unripe in its green form, it has less sugars and it tastes sour. So you can already see that the bar value is quite low. There's low sugar and high acid. But as the fruit ripens, what happens is that the sugar concentration increases while the acid decreases. But we actually want a certain balance whereby that combination in terms of content is going to provide us with that tartness flavor. Because what happens is that when the fruit starts becoming overripe, it increases in sugar and with no acid, so it then lacks that characteristic flavor. There must be that acid ratio. So same applies to, obviously the fruits are then used to produce other products, especially fruit juices. So we still want to maintain those characteristics, because in food products we then rely on the acid that are naturally in the fruit itself, but then we also rely on the acid that we also add in the food just to maintain that. Okay, so when you are doing the bar value, the Brix-Acid Ratio value, it's a two-step process whereby the first part of it is measuring the sugar concentration using your refractometer. I mean, I think everybody knows how to do this. You just have your refractometer and then you check the Brix and it tells you it's 20%, 30 or whatsoever. And secondly, then you do what we call the titratable acidity. So I'm not going to explain anything in terms of how to measure sugar concentration. You guys all know that. But what I'm going to dwell on is the measuring of the titratable acidity. Because remember we said it's sugar and the acid ratio. So the acid part is what I'm going to dwell more on. So when it comes to the titratable acidity, there are two methods. There is two methods, because if we're talking about acids always go with bases. So the first method will be what we call an acid-base titration. And this acid-base titration is actually suitable when you have clear juices, because you just have your acid that's already in the juice. We don't know which one. I'm going to explain just now. And then when you have the base that we normally use is sodium hydroxide. So this is where you actually have your phenolphthalein as an indicator, whether it changes pink or changes from pink to colorless. So it means that it is only suitable or more suitable when you have clear juices, so that you can actually see the end point. Because usually when you have juices like your apple juice and maybe your dark orange juice, then what happens is that it's not easy for you to see the end point. So that is why then the second method becomes more preferable, whereby you're using a pH meter. It's called the potentiometric method, using the pH meter, whereby you adding the base and then you are monitoring the change in pH, the neutralization point, which then you just have to look at the values that are displayed on the pH meter without having to worry about any color change. So those are the two that I'm going to explain about. So as we already mentioned that your titratable acidity is determined by acid-base titration, and we said we use sodium hydroxide. And then what that does is it then measures the total concentration of acids, especially your organic acid. So the organic acid, you have your citric acid, your malic acid, lactic and tartric acid. And then also sometimes those ones, your citric, malic, lactic and tartric, will be inherent, will be natural in the fruit itself. And then in the food industry, we also have phosphoric acid, which is then added into the food. So those will be the different types of acids. So know that in terms of different fruits have different types of acids that are predominant in there. Like when we're talking about lemon and limes, we know that it's actually citric acid. But when we talk about apples, your apples will then give you your malic acid. So that depends on the fruit. So what happens is that, as we already mentioned, that the importance of this titratable acidity is that we mentioned that these acids, they contribute to the flavor, and not just the acid only, the acid plus the sugar, because if we take away the sugar, the juice will just be sour, and that wouldn't be nice. So the combination and the ratio of those two influence the tartness, and besides the flavor component of this, they add obviously to the color of the juice. And very important, microbial stability, because we already know the minute you add acid, you are increasing the acid level, you are decreasing the pH, and then usually most microorganisms like your bacteria are not, those pHs are not favorable for them. So in that way, you're increasing the shelf life or the keeping quality of the fruit. So it's not just the flavor, but also other properties or functional properties that are required in food. So how do we go about determination? Very easy. So what happens is that we have a known volume of food. Let's say you have 15, 20 mils or 30 mils of your juice. That is, we want to measure the titratable acidity, and then we titrate that against a standard base, and that is usually your sodium hydroxide. So sodium hydroxide will be in the burette, and then your juice sample, or whatever sample that you are measuring, you want to measure or determine the titratable acidity, will be in an Allen-Meyer flask. So then you can then insert a pH meter in there and then titrate with the acid until it reaches the point of being neutral between pH 7 and 8. Or you can then be using your phenolphthalein that you add in the juice, and immediately when you reach the neutral point, it's going to turn pink, because phenolphthalein turns pink with the base and then it's colorless in your acid. So that known volume, so the volume of the titrant, and then it's used to calculate the titratable acidity expressed in terms of the dominant acid. You will see with the calculation whereby you're going to take into consideration the volume of the sample. You take into consideration both the volume that you use to titrate and then the concentration of that standard sodium hydroxide or base, and then also the calculation you have to bring in the molecular weight of your predominant acid. And that is something that you need to know, that okay, if this is orange juice, then we know we are working with citric acid, but if it's then apple juice, we're working with malic acid. So that will be the information that you know, and then you can do the calculation. So some general consideration is that in terms of your product, depending on the product, you have to choose whether you want to use the titration with using your phenolphthalein indicator, or you want to use the pH. And as I already mentioned, that very important, I would always prefer to use the pH meter, because it will be more accurate, especially if there is some color components of my from that's coming from the actual product. And then also the buffering can interfere with the reading of the end point, so that will then become a problem there. And then we already mentioned that also at the same time, when we're using the titration method, when the pH meter is used to determine the endpoint, it's very important that the equivalence endpoint is the number of acids that's equivalent to the number of base, so that's where neutralization takes place. However, one of the problems would be, as we already know, that your sodium hydroxide is highly hygroscopic, so the concentration can change thereof if it's just left there, and then you will have the wrong readings because of the wrong concentration that has changed over time. Okay, so then as I already mentioned, that the color change will be around pH 8 and 9.6, and then I had mentioned that if you have buffers in the product, you might have problem with reading the endpoint. Remember, buffers don't allow change in pH, so you keep on adding and adding. Meanwhile, the pH is not changing, only because there's buffer in there, then you actually get results that are wrong. Okay, so what happens, we mentioned that the color change can also take place between 8 and 9.6, and as I already mentioned, most food acids do not buffer in this region. Exception will definitely be phosphoric and carbonic acid, and therefore, as a result, then for these type of organic acids, it's better to use the pH method than the actual titration method, where you might not get to the right endpoint. And then I'm going to try and make this again, mention this, that are deeply colored samples, then they're very dark, especially your freshly squeezed samples. The endpoint is different to see, because then you will be adding your phenolphthalein and you add your sodium hydroxide, but because the sample is dark, you can't see the endpoint. Remember, when you are titrating clear solutions, it is actually that faint pink color that persists for more than 3 seconds. So maybe from between 3 seconds and a minute. So if it's dark, how are you going to see that faint pink color? So that's why the pH is much more required, or much more preferred, so that you don't get any errors. And then also your indicators that you use may influence the sample analysis, as they are usually weak acids or base thereof. So 2 to 3 drops maximum are added, but sometimes somebody would add 1 drop, and then you don't have enough of the indicator to then show you if there's any neutralization taking place. Okay, so we already mentioned sodium hydroxide is always used, and I mentioned that it's highly hygroscopic. It can also react with carbon dioxide and with glass and plastic. So by doing so, it changes its concentration. So that is why it has to be standardized to get the actual concentration, and we usually standardize it with another acid. That way it helps so that we know the exact concentration thereof of the prepared one, because remember I mentioned that we use that concentration to calculate the titratable acidity. So if your concentration changes from 0.1 to obviously can go to 0.6, or maybe 0.1 to 0.07, then already you are already out in terms of your calculation. So that is why you need to standardize the sodium hydroxide. Okay, and then the procedure that I'm talking about is what we actually going to do in the virtual practical. And then we mentioned that the TA is then stated in terms of the predominant acid in food. So it might happen that you use an example, let's say it's apple juice, but then you use the predominant acid as citric acid, then your results will be wrong. So it means that you need to know for sure which acid is predominant in that fruit for you to be able to then calculate the TA. So here it is. We mentioned that the bar value considers the value of the acid, or the ratio between the acid and the sugar. And then the acid tends to decrease with maturity and sugars increase. That is why an overripe fruit is not nice. It's too sweet without the tanginess. I've mentioned that. So now when you're calculating the bar value, it's actually the degree Brix that you would have obtained using your refractometer divided by the percentage titratable acidity. So the larger the bar, it means this is a more mature, sweeter fruit. But then it means we have to go to the actual way of calculating your bar value. What happened to that slide? Okay, so I'm just missing how the titratable acidity calculations. Okay, that you can find in your, I thought I have put in here, that you can find in your practical manual. So you will calculate the Brix, obviously, you will determine it, and then you will divide it by the percentage titratable acidity. I'll emphasize more of this in the actual practical. I thought I had it here. And then lastly, we have what we call your volatile acidity. Volatile acidity is related to your TA. However, it actually considers the contribution of acetic acid to the total acidity. So how to go about determining this volatile acidity? You first perform the titratable acidity reaction, and then from there, once you have done that, you take the juice and then you boil it. By boiling it, you are actually driving off the acetic acid. And then from there, after doing that, then obviously you have to cool it down, and then you redo the titration. And this is known as the fixed acidity. So then the difference between the titratable acidity and then the total acidity brings you the volatile acidity. Okay, and then other methods that can be used are your HPLC method, high performance liquid chromatography, but obviously that takes time. You are in the lab, you just want something that is quick that you can calculate. Okay, so just done there. This is just showing you concentrations and units, the different concentration that you will definitely see in your, what is this, in the practical manual, that you will actually definitely come across, not just with this practical, with all the other practicals, where you can see the molarity, the normality, equivalent weight, percentage concentration, parts per million and parts per billion. So those will be the molarity. You know how to calculate the molarities, number of moles over a liter of solution, the equivalence number, molecular weight divided by the number of the equivalents, and then you divide that by 2. Percentage concentration, we all know about that. It's either by volume or by weight. You probably did this in processing engineering and mathematics also. So a gram per 100 gram, that will give you percentage, or a gram per 100 mil, or a mil per 100 mil. And then we talk about parts per million, which happens to be your milligrams per kilogram. And then we also talk parts per billion, that will be your micrograms per kilogram. So those are the types of concentrations and units that you need to get used to, that we apply in food science and technology. And then we also talk about equation for neutralization and dilution. You know, when you are diluting, then you can say 1 part to 3 parts add this. That's the dilution. And then we also talk about the neutralization of acid-base reactions. You know when an acid and a base react together, what is usually formed is salt and water. Okay, so that will be the neutralization. Very important. You need to be able to determine the type of the acid that is. You have what we call your monoprotic acid, your diprotic acid, and your triprotic acid. So when you're doing the C1, V1, C2, V2, you need to also take into consideration the type of acid that you're working with, in terms of how many of those protons do they have, or your acid groups, put it that way. Thank you very much.